Have you ever stopped to wonder why the sky is a brilliant blue in the middle of the day, but then slowly transforms into a fiery red, orange, or pink when the sun sets? It feels almost magical, but in reality, it's the result of physics, chemistry, and the way light interacts with our atmosphere. This transformation of color isn't just beautiful, it's a story about sunlight, particles, and the invisible forces shaping what we see every day. The sun may look white when you glance at it in the sky, but sunlight is actually made up of all the colors of the spectrum combined. You can see this in action if you've ever looked at a rainbow or light passing through a prism. Each color of light corresponds to a wavelength. Blue light has a shorter wavelength, while red light has a longer one. The way these wavelengths behave as they travel through Earth's atmosphere is what determines the color of the sky at any given time. When sunlight enters our atmosphere, it doesn't just pass straight through. It collides with gas molecules, tiny particles, and dust floating in the air. These collisions cause a process called scattering. Not all colors scatter the same way. Shorter wavelengths like blue and violet are scattered much more strongly than longer wavelengths like red and yellow. In fact, blue light is scattered nearly 10 times more efficiently than red light. This phenomenon is known as Rayleigh scattering, named after the British scientist Lord Rayleigh, who first explained it in the 19th century. So why does this make the sky look blue during the day? As sunlight passes through the atmosphere above us, the shorter blue wavelengths are knocked around in all directions. Your eyes receive that scattered blue light from every part of the sky, not just from where the sun is located. That's why the whole dome above your head takes on that bright blue appearance. Violet light actually scatters even more than blue, but our eyes are less sensitive to violet, and some of it is absorbed by the upper atmosphere, which is why we perceive the sky as blue rather than purple. Now what about sunset? Why does the sky shift from blue to red and orange when the sun is close to the horizon? The key difference is the path length that sunlight has to travel through the atmosphere. At noon, when the sun is overhead, light only has to pass through a relatively short column of air to reach your eyes. But as the sun lowers toward the horizon, the light must travel through a much thicker layer of atmosphere. That extra distance means that most of the shorter wavelengths, blue, violet, even some green, are scattered completely out of the line of sight before they ever reach you. What remains is the longer wavelength light, reds, oranges, and yellows. These colors survive the journey through the dense atmosphere and paint the sky in those warm hues that we associate with sunrise and sunset. Dust, pollution, and even volcanic ash can intensify this effect. When there are more particles in the atmosphere, scattering becomes even more pronounced. Instead of just removing the blue light, these extra particles scatter and filter the remaining colors, often producing more vivid and dramatic sunsets. That's why sunsets can look especially stunning after a storm or in areas with higher levels of aerosols in the air. In contrast, in places with cleaner air, sunsets might appear paler and less fiery. The position of the sun and the thickness of the atmosphere aren't the only influences. Humidity and water vapor can also play a role, bending and diffusing light further, which adds to the richness of the colors you see. This is why a sunset over the ocean can often look different from one in a dry desert, even though the same physics is at play. Interestingly, the same principle explains other phenomena you might have noticed. For example, when astronauts look at Earth from space, they don't see a blue sky, they see the blackness of space. Without an atmosphere to scatter sunlight, there is nothing to give the sky its daytime color. Similarly, on Mars, sunsets look bluish rather than red because of the unique dust particles in the Martian atmosphere, which scatter light differently than our planet does. So the colors of the sky aren't random or simply aesthetic. They're the visible outcome of the interaction between light and matter. Every time you see a brilliant blue noon sky or a glowing red sunset, you're witnessing physics in action, an atmospheric filter separating and scattering light wavelengths before they reach your eyes. When you put all this together, the story becomes clear. The sky is blue during the day because the shorter wavelengths of sunlight are scattered in every direction by the molecules of the atmosphere, dominating our view. At sunset, the light takes a longer path through the atmosphere, removing the short wavelengths and allowing the longer red and orange wavelengths to remain, transforming the sky into a warm and colorful spectacle. This daily shift from blue to red is more than just a beautiful view. It's a reminder of the delicate balance between Earth, its atmosphere, and the sunlight that powers our world. The next time you find yourself watching the sky at dusk, you can appreciate not only the beauty, but also the remarkable physics behind it. What looks like art painted across the horizon is, at its core, the science of scattering, wavelength, and perspective. And that's why the sky is blue during the day, but turns red at sunset.